In this lesson, we are going to learn the integral test for infinite series. This is a test you can use to try to show that an infinite series converges or diverges. So we'll see that when we look at the statement of the integral test. Then we'll work through a few examples, including the famous p-series examples. The p-series analysis gives rise to essentially a second test that you could call the p-series test. I think it's important to see visually why the integral test is true. So we'll do kind of like a picture proof of the integral test, and then we will also look at how to estimate the error for a partial sum for a series that you've analyzed with the integral test. It's another picture. It kind of follows nicely from the proof, but we will include with that an example. Here's the integral test for infinite series. Suppose we would like to analyze a series whose terms look like a sub n. We want to know if this series converges or diverges. If we can write down a function of the form y equals f of x, where this function is continuous, positive, and monotone decreasing on some domain starting at what I'm going to call k, I'll explain that in a second, and going off to infinity, if we can write down such a function and compute its improper integral, then if that improper integral converges, our series converges. If, on the other hand, the improper integral diverges, then the series diverges. So what we're going to do is take our series terms and basically turn it into a function and then do an improper integral. The reason why I've made this strange choice of describing my domain as going from k to infinity is that maybe your function f initially doesn't have the properties that it's continuous, positive, and monotone decreasing. We'll see an example of that. However, beyond a certain value of x, it does have those properties. Then that's good enough. So what you do is pick the domain on which f satisfies the necessary conditions, and then you do your improper integral. So as long as you can find some positive lower bound so that this improper integral can be shown to converge or diverge, then we can analyze our series. I'll just note here that often k is 1. Okay, so let's look at some examples. Let's see if we can use the integral test to analyze the series whose terms look like ne to the negative n squared, where we're adding up the series from n equals 1 to infinity. What we're going to do is take that series expression and turn it into a function exactly like you expect. So everywhere I have n, I'm going to replace it with x. We'll say let f of x be the function x e to the negative x squared. Here's a graph of that function. So you can see that on the domain from 1 to infinity, this function is continuous, positive, and monotone decreasing. Therefore, it's a good function to test with the integral test. We need to do the improper integral from 1 to infinity. So let's say that we're going to integrate from 1 to infinity f of x dx. We want to know if this improper integral converges or diverges. We don't really care what its value actually is. We just want to know, does it converge or diverge? Okay, since this is an improper integral, what I'm going to do is take this top bound of infinity and replace it with the letter t. And then we'll take the limit as t goes to infinity. So we're integrating 1 to t, x e to the negative x squared with respect to x. Okay, this is a u sub situation. So if I let u be the negative x squared, then du is negative 2x dx. I'm going to write that as negative 1/2 du is x dx. Okay, so I'm going to put this here. This will be the limit as t goes to infinity. I need to change my bounds, but first let me change my integrand. E to the negative x squared becomes e to the u, and then x dx becomes negative 1/2 du. We need to change our bounds. So we say, well, what was the lower bound? It was 1. If I plug that in for x, u would be negative 1 squared, so that's negative 1. And then for the top bound of t, if I plug that into x here, u is negative t squared. Okay, so that is our new integral after the conversion with u substitution. Let's antidifferentiate. It's the easiest antiderivative possible. So this is the limit as t goes to infinity of negative 1/2 e to the u, where the bounds go from negative 1 to negative t squared. So we'll do the limit as t goes to infinity of -1/2 e to the negative t squared minus -1/2, so I'll write +1/2 e to the -1. Okay, let's take a look at this. When t goes to infinity, negative t squared goes to negative infinity. The exponential function as you go down to negative infinity shrinks to 0. So this first expression here, this goes to 0 as t goes to infinity. That means that this improper integral converges. The value of this improper integral is 1 over 2e. Be careful here. That is not the value of the series, it's the value of the improper integral. We'll relate how to compare the values of the integral and the series later when we do the quick proof of the integral test visually. For now, let's just say that this converges. Since the improper integral converges, the series converges. And that's how we use the integral test. Now let's look at the infinite series whose terms have the form natural log of n minus 1 all over n squared. The natural thing to do here is to write let f of x equal natural log of x minus 1 all over x squared. Here's a graph of this function. What you will notice is that if we look at x equals 1, x equals 2, where we start our infinite series, then the function is not decreasing and it's not positive. However, if we go out far enough, then our function does have the necessary properties. It's continuous, decreasing, and positive. So that means that when I do my improper integral test, I don't want to start with a lower bound of 1, even though that's where my series starts. I would like to start somewhere where the function has the necessary properties. I'm going to pick 10. So we'll analyze this function on the domain from 10 to infinity. That's good enough. If that converges, then our series converges. If it diverges, then our series diverges. So let's go ahead and set up the improper integrals, the limit as t goes to infinity of the integral from 10 to t. So I'm picking a lower bound of 10, and that's t. Okay, then we'll do natural log of x minus 1 over x squared dx. You can experiment with this integral for a minute. You can try u substitution or something like that. This is an integration by parts integral. I will let u be the numerator because natural log gets a lot better after differentiation. So we'll say, I'll do it over here. Let u be natural log of x minus 1, so that du is 1 over x dx. On the other hand, have dv be 1 over x squared dx. I will write that as x to the negative 2. Just helps me do the power rule. So dv is x to the negative 2 dx. So that v is x to the negative 1 times 1, or times negative 1. So v is negative 1 over x. Okay, so that's going to be our integration by parts approach. Integration by parts gets pretty large, so I'm going to slide this over here. We are going to be taking the limit as t goes to infinity. I'll leave this on the outside of, now for the first part of integration by parts, I need to do u times v. Overall, that's going to be natural log of x minus 1 times negative 1. I can multiply this by negative 1 if I flip the order of the subtraction there. So I'll write 1 minus natural log of x all over x. Okay, so that's what you get when you multiply u times v. We need to evaluate this from 10 to t. And then we have minus negative 1 over x squared dx, and that's from 10 to t. All right, let's go ahead and plug t in here, anti-differentiate here. So this will be the limit as t goes to infinity of 1 minus natural log of t all over t, and then minus 1 minus natural log of 10 divided by 10. 1 minus natural log of 10 divided by 10 is just a number. This first part we'll need to analyze as t goes to infinity. Going on to the second part here, we will have minus 1 over x. I'll check that in a second, going from 10 to t. Okay, so let's make sure I did the right thing here. This is x to the negative 1. If I bring it down, that becomes positive x to the negative 2. Yes, I think that looks right. Okay, so what we will do here is leave this alone. This is a number. This is an indeterminate form. As t goes to infinity, the top goes to negative infinity and the bottom goes to infinity. So I will do L'Hopital's rule on this expression. So this is going to get L'Hopital's rule. One round of L'Hopital's rule should give it to us. And then I'll go ahead and plug in for that one as well, so that this is the limit as t goes to infinity of, we do L'Hopital's rule here, we get negative 1 over t in the numerator divided by 1. Okay, and then this is minus 1 minus natural log of 10 divided by 10. And then I got to watch my signs here, but this is going to be minus 1 over t minus negative, so plus 1 over 10, which is just another number. What happens to this expression as t goes to infinity? Take a second to arrive at the conclusion and apply the integral test. As t goes to infinity, 1 over t goes to 0. So this first term goes to 0. This term also goes to 0. So we have negative 1/10 plus natural log of 10 over 10. I split that up. Plus 1/10. The 1/10s cancel. So that overall, this improper integral converges. I'm just going to make a note here that these go to 0. This improper integral converges, and it actually has the value natural log of 10 over 10. So we conclude that everything converges. The improper integral converges. Going back to our series, if we started our series at n equals 10 and let n go to infinity, that would be the series for which this would be the most natural test with the integral test. However, the first few terms in a series never affect convergence. So whether or not a series converges depends on the behavior as we go out in the series. It doesn't begin on how we start. So if the series from 10 to infinity converges, the series from 1 to infinity converges. So this test is good enough to know that this series converges. The integral test gives rise to another test, which we see so often that it deserves its own name. And it's something that whenever we see it, we're not going to revert to improper integration because we're going to recognize it and apply this test immediately. This is called the p-series test. And what it tells us is if you're looking at a series of the form 1 over n to the p, where n, the base here, is the index, and p is a fixed number. So it might look like 1 over n squared or 1 over n to the 13.5. This is called a p-series, and it converges if and only if p is greater than 1. So if p is greater than 1, you have convergence. If p is less than or equal to 1, you have divergence. I'm actually not going to spend any time justifying this test because we already did this when we looked at improper integrals. So in an earlier video, we showed that the integral from 1 to infinity of 1 over x to the p dx, this improper integral converges if and only if p equaled 1. So we worked through all of the details of that when we looked at improper integration. So the convergence and divergence of this family of improper integrals is equivalent to the convergence and divergence of this family of infinite series. And then I just want to make a remark here that there's a very famous divergent series called the harmonic series, which is actually a p-series when p equals 1. This series we looked at and we actually proved it diverged in the video on the test for divergence. Each of these three examples is a p-series, so let's use the p-series test to deduce whether or not these converge or diverge. This first one, we're looking at 1 over j squared, starting from j equals 5 and going off to infinity. Wanted to mix up the indices here, how I name them, because I so often use the letter n, but of course we could call it j, we could call it k, like in the second example. So this series, if I start to expand it, it's going to look like 1 over 5 squared plus 1 over 6 squared plus 1 over 7 squared, and we continue that forever. So notice here that the base corresponds to the index going from j equals 5 off to infinity. So that's what's changing with every new term in the series. The exponent is fixed at 2. Here, this is p series with p equals 2. So we can say converges by the p series converges by the p series test with p equal to 2. For the second example, we have 1 over the square root of k. And we're going to add this up from k equals 1 off to infinity. So this would look like 1 over the square root of 1 plus 1 over the square root of 2, etc. And you might not immediately recognize that this is a p-series, but we need to take these square roots and interpret them as exponentiation to the 1/2 power. So this is 1 over 1 to the 1/2 plus 1 over 2 to the 1/2. So here, the base is what's changing each time, and the exponent is fixed at 1/2. That makes this a p-series. This diverges because p is 1/2. That's less than or equal to 1, and therefore it's going to diverge. For this third example, this is pretty much written exactly as a p-series. I just put a coefficient or a constant of 3 in there. That doesn't affect the convergence. This is really 3 times the convergent series from n equals 1 to infinity of 1 over n to the 4. This converges immediately. We see that because this is a p-series with p equal to 4. Okay, so these are the kinds of terms that you look for when you want to apply the p-series test. We will use p-series also to analyze similar series expressions when we look at comparison test. So how I like to think of p-series is p-series gives us another series whose convergence or divergence we can immediately recognize. It should remind you of the geometric series. So if you're looking at a series, you recognize geometric series, recognize now p-series, and know when they converge and diverge. Okay, let's look at the visual justification for why the integral test works. Imagine we have this function f here, which is continuous, positive, and monotone decreasing. What we're going to do is two Riemann sum approximations for the area under the curve. What's neat here is that the way that we chop up the x-axis in order to make rectangles to estimate the area under the curve, we're going to do this in a way so that the rectangles all have width 1. So in particular, on these axes, all of these slice points are the values 1, 2, 3, 4, 5. They're the terms that we plug into the function in order to generate the terms that we add up in our series. So what that means is if you look at the widths of each of these rectangles, what we would call delta x in our Riemann sums computation would be just 1. So notice delta x is 1. It's the spacing between whole positive numbers. So if you look at this picture here, we have a right endpoint estimation because over each subinterval along the x-axis, I've chosen the right endpoint and then graphed the height of the corresponding rectangle so that we get these rectangles which sit under the curve. Let's write down what that right endpoint estimate would look like as a Riemann sum. The right endpoint estimate which is going to be the sum of the areas that I've graphed over here on the left. This is going to be the sum, let me write down the indices in a second, of f of, well, I'm adding up f at the right endpoints, and each of those endpoints is a whole number. Because of the way that we subdivided the x-axis, we made our sides of the rectangles correspond to the numbers 1, 2, 3, 4, 5, 6, et cetera, et cetera. So it's going to be f of n delta x. But then notice that the first whole number generating the first right endpoint for this estimation is happening at n equals 2. So this is from n equals 2 to infinity. Now the thing is, f of n is exactly the series term a sub n. And then delta x is 1. So the conclusion of setting up this Riemann sum computation is that the area pictured on the left is equivalent to an infinite series. It's just the series a sub n from n equals 2 to infinity. Okay, so let me give you a moment to process that, and then we will look at how to set up a Riemann sum for this other picture. If you'd like, you can go ahead and see what you get if you do the left endpoint estimate. Okay, for this picture on the right, we have the same subintervals along the x-axis. So we're starting with n equals 1, n equals 2, 3, 4, 5. But this time, I've chosen the left endpoints of each subinterval to generate the heights of all of the corresponding rectangles. Once again, delta x is still 1. The width of each of these rectangles is 1. So let's set up the left endpoint estimation. For this, it's going to be the sum. Again, I'll write down the indices in a second, of f at an integer value, delta x. But what is the first integer for the first whole positive number that we plug into our function? In other words, what is our first left endpoint? It's actually happening when n equals 1. So this time we're going to index from n equals 1 to infinity. Once again, f of n is the series term a sub n. It's what we're adding up. So this turns into the series from n equals 1 to infinity of the terms a sub n times 1. In other words, this is the whole series. This is the series without the first term. So let me add this here. Okay, so we have that this area with the right endpoint estimates is equivalent to taking our infinite series and adding it starting with the second term. This area here is equivalent to adding up our series starting at the beginning. Notice that the true area under the curve sits between these two. So the right endpoint estimate is a lower estimate. The left endpoint estimate is an upper estimate. That's because our function is continuous, positive, and monotone decreasing. So since it's decreasing, right endpoints are under, left endpoints are over. So what I'm trying to say is that between these two sums is the improper integral from 1 to infinity of this function. So the integral test gave us that the convergence of this integral implied the convergence of this series, and the divergence of this integral implied the divergence of this series. Let me explain why that would happen. If this integral converges, then this sum has to converge because it is smaller than something which is converging. The terms here are positive, right? So we're just adding positive numbers. So if this adds up to something finite, this adds up to something finite. And since this is essentially the same series, it's just missing one number. If this adds up to something finite, then the whole thing would add up to something finite because we just add one more number. So this converging tells you this converges. On the other hand, if this diverges, because this area under the curve gets larger and larger without bound, you could say it's like infinite area. If this diverges, this is greater than or equal to that. So if this goes to infinity, this goes to infinity. That's why the behavior of the improper integral, whether it converges or diverges, gives you the behavior of the infinite series. Suppose we have an infinite series, which we know converges by the integral test. So let S denote the true sum of the series. Now consider any partial sum, which I'll denote S sub n. Careful here because I'm indexing my partial sums using the letter n, which means that I want to switch my indexing in my series from n to j. So that's why there's a little bit of a letter change here. But the nth partial sum is going to be the sum of the first n terms. We are not adding up the whole series, so there's some remainder left over. Let's let R sub n denote the remainder. So that's S minus S sub n. And given that this is a sum, this is a sum, I can actually write the remainder as a sum. What would happen is if I subtracted my partial sum from the true sum, we would just cancel out all of the terms that they have in common, which is the first n terms from the series. So this remainder can be written as the sum from j equals n plus 1 to infinity a sub j. It's all of the remaining terms. What is the size approximately of this remainder so that I can get a feeling for how good my partial sum is? Well, just like when we looked at the proof of the integral test, we can figure out how to estimate this error, how to give a bound on its size using just visual pictures and tying the integral test over to, say, Riemann sums. So first look at this picture on the left. I have imagined that I've added up until the nth term. So the nth term is in my partial sum, which means that this number here, this like top right corner of my first rectangle, that's the number a sub n plus 1. This next one is the number a sub n plus 2. Just like before, the widths of each rectangle is 1. So that means that the area of this first rectangle is height a n plus 1 times width 1. It's the number a n plus 1. Okay, so let's do picture on the left. The total area of the rectangles in this picture is the number a n plus 1 times the width 1. That gives me the first rectangle. And then a n plus 2 is the height for the second rectangle times its width, which is also 1. And continuing in this way, you see that the sum of these areas is equivalent to the remainder R sub n. However, now compare these rectangular areas to the graph of the function that we have, which is starting at n and going off to infinity. Because I start at n, this point, this right endpoint, is providing an underestimate for the area enclosed between the x-axis and the graph of this function. In other words, all of these rectangular areas are under the function. And so this sum of areas here is less than or equal to the integral of our function starting at n and going to infinity. Okay. So to repeat myself, because I don't think I said it very clearly just now, I'm concluding that all of these rectangular areas sum up to the value of our remainder. But because in this picture, each rectangle is being determined by right endpoint for this decreasing function, this area sum is an underestimate to the true area under the graph of this function starting at x equals n. Contrast that to what's going on over here in this picture on the right. So let me say, pick on right. Here, this point is still n plus 1. And now I'm basically going to estimate the area under the graph of this function starting at x equals n plus 1 using left endpoints. So this is going to be a different integral, but it's the same rectangular comparison where this first function value I've picked here, this left endpoint, this is at the height a sub n plus 1. And once again, the width is 1. So the area of this first rectangle is a sub n plus 1 times 1. Maybe I should put that here as well. So here we have a n plus 1 times 1. Here we have a n plus 2 times 1. We're getting the same sum actually that we had over here. So these rectangles also add up to the remainder. In fact, if you can kind of remove the function and just compare the rectangles, you'll see they're the same rectangles. On this picture, though, notice that if I integrate my function starting here at the value x equals n plus 1, so I'm going to start my integral 1 unit to the right compared to on this picture. This time, our areas are overestimates. So each of these rectangular areas is sitting under the graph, or sorry, sitting over the graph of the function because the graph of the function is kind of cutting into them. So this is greater than or equal to starting the integral at n plus 1 and going off to infinity. Okay, so let me combine both of these inequalities now. I'm going to write it in ascending order. So the smallest quantity we have is the integral from n plus 1 to infinity of f of x dx. This integral is less than or equal to the size of our remainder is less than or equal to the integral from n to infinity of f of x dx. The reason why this bound is important, why we need to work out this kind of quantity, is because we might not know the true value of our sum. The only quantity that I might be able to add up here is the partial sum. I don't know the true sum. So if I don't know the true sum, I can't tell you the true remainder. But if we're using the integral test here, presumably we can do these integrals. So if I can do these integrals, then I can say that the remainder sits between them. That can give me, say, in particular, an upper bound on the size of the remainder, giving me an idea for how close my partial sum is to the true sum. Let's use this remainder computation to provide a partial sum for this convergent p-series, and then we'll estimate the size of the remainder, and then we'll figure out how many terms we would need to guarantee that the remainder is suitably small. For us, that will be 0.0001. So I call this a convergent p-series because it has the form of a p-series where the exponent p is 4. Since 4 is greater than 1, we know this converges. Unlike a geometric series, though, we don't have a closed form expression for this particular p-series, at least not one that I know. So a p-series is something that's not easy to add up. Let's estimate it with a partial sum. So first, let's find the partial sum s sub 6. That's going to be the sum of the first 6 terms. I'll write it out so that we can focus on what changes and what doesn't change with a p-series. So this is 1 over 1 to the 4th power plus 1 over 2 to the 4th power. It's 1 over 3 to the 4th power. Just be careful with the p-series that you are changing the base, not the exponent. Okay, I had to write this down. This is approximately 1.0811. Okay, I had to do some rounding there, but let's give this as an approximation of our partial sum. Okay, so what is the upper bound for the remainder? I want to know like the worst case scenario for the remainder. Let me do this in generality for the remainder for any partial sum, and then we'll focus on this partial sum in particular. For S sub n, based on the demonstration that we just did, we know that R sub n is less than or equal to the integral from n to infinity of the function which looks like these series terms. So that's 1 over x to the 4 dx. This is an improper integral, so let me switch this to the limit as t goes to infinity of, you know what, I'm going to go ahead and anti-differentiate as well. So this is x to the negative 4, so that's x to the negative 3 times negative 1/3, going from n to t. Okay, so I skipped a step here, but rather than rewrite this, just replacing the upper bound with t, I went ahead and kind of mentally did that, anti-differentiated to get negative 1/3 x to the negative 3, and then when we plug in our top and bottom bounds, the top one is what I'm now calling t. Okay, continuing on to the right, this is going to be the limit as as t goes to infinity of negative 1/3 t to the negative 3. So that's negative 1 over 3t cubed minus negative, so plus 1 over 3 n cubed. All right. This should converge because this is a convergent p-series. It corresponds to a convergent improper integral, and indeed that is what's happening. That is what's happening, excuse me, because this first term as t goes to infinity is going to go to 0. All right, so the result of this is that in terms of the index on our partial sum, the remainder is bounded above by 1 over 3n cubed. This would allow us now to do the remainder for any partial sum, including s sub 6. So down here I'll say thus, the remainder for our sixth partial sum is less than or equal to 1 over 3 times 6 cubed, which, if I computed this correctly earlier, is, I can't remember if I rounded down or up, but this is about 0.0016. So it's pretty close. That would tell you that the sum, the true sum of this convergent p-series, is no larger than s sub 6 plus this remainder. So 1.0811 plus 0.0016. We could say s is less than or equal to s sub 6 plus r sub 6. And that would give you an approximation of the overall series. Okay, I'll step aside and let you think about this computation. And then what we would like to do is say, imagine we want our sum to be very good, or our partial sum to be a very good approximation of our sum. How many terms would we need to guarantee that the maximum error size would be less than, say, 0.0001? Okay, I kept the one piece of information that we need from the first part of this problem in order to solve the second. We found an upper bound for the remainder for the nth partial sum. We said the remainder was less than or equal to 1 over 3 n cubed. Now we want that to be less than 1 over 10,000. Okay, so that's 0.0001. Don't know why I'm struggling to say 0. Okay, let's take the reciprocal. So 3n cubed is greater than 10,000. Okay, so then n cubed is greater than 10,000 over 3. If you take the cube root of that, you get something like n is approximately 14.9. That doesn't make sense because n is an index. We want to know how many terms do we need to guarantee that the remainder is no larger than 1 over 10,000. So we always need to round this up. Whether it's 14.1 or 14.9, we should round up. So we would want to add up 15 terms in order to know that our partial sum was suitably close.